Okay, so what this means is with this new term, the mole, right? We have the ability to um, identify how many grams of a material we'll need to make them equivalent to each other. So 6.02 times 10 to the 23rd, that's the number of whatevers in a mole of whatever. Like 12, 12 is what?
Well, that's a dozen.
12 is a dozen, and the mole is now what?
6.02 times 10 to the 23rd?
That's right, 6.02 times 10 to the 23rd. And the reason we got that number is because if you take 12 grams of carbon 12, so here's carbon 12, we take 12 grams of it, and the number of atoms that we have is this 6.02 times 10 to the 23rd atoms of carbon. Okay? So if I look at chromium here, chromium, how many grams do I need to get a mole? Well, the answer is this 52. 52 is how many grams I need to get a mole. And why that becomes helpful to us is because now that number on the periodic table for chromium or for any of the other elements, right, is how many grams you need to weigh out to have a unit of it, and we call that unit a mole. All right? So this can be true of not just elements, but any chemical, right? We can find what we call the molar mass, the mass in terms of moles, how many mass you need to get a mole of it, or molecular mass or molecular weight. Sometimes on chemical bottles you'll see it abbreviated FW or MW, which means formula weight or molecular weight. Now, it shouldn't be weight, it should be mass, but sometimes you see it this way. And this becomes helpful because I can then know exactly how much of each of the different components I'm going to need to have if I want to perform chemistry and have enough of whatever. So for example, if I want to perform a chemical reaction where I determine how much carbon dioxide is taken up, maybe I have a plant and I think that this plant will be wonderful at curbing global warming, and so I'm going to see how much carbon dioxide it consumes. And I'm going to put it in an environment of carbon dioxide, and I want to know how much uh, carbon dioxide to put in there, right? I need to start off with the right amount of carbon dioxide. Well, one way to do that would be to have a fixed amount of carbon in here, burn it in the presence of oxygen, and not enough oxygen, and then I would know exactly how much carbon dioxide I started with, and from that I could determine how much carbon dioxide the plant is consuming. So if I wanted to get a certain number, a certain mass, let's say I want 44 grams of carbon dioxide, I would know exactly how many grams of carbon and how much oxygen I would need to get that 44 grams. All right. Uh, if I want 44 grams of carbon dioxide, I can determine how many moles of carbon dioxide that is. All right. Because this equation here says 1 mole of this plus 1 mole of this will yield 1 mole of this. All right. You see that's my chemical equation. And the coefficients, which I don't have any numbers in front, so this just means 1, tells me if I want 1 mole of carbon dioxide, I need to consume 1 mole of this and 1 mole of oxygen gas. So how many moles is 44 grams of carbon dioxide? All right. Well, I need to identify how many grams of carbon dioxide equals 1 mole. And the way I do that is I take the masses of the different elements in a unit of carbon dioxide. That's 1 carbon and 2 oxygens. Carbon, I can look on the periodic table and see that it's 12, 12.0. 1 carbon, that's 12.0. 2 oxygens, each oxygen is 16, so that's 32.0 there. And so then I can add these together, and I see that 1 mole of carbon dioxide is equal to 44 grams, the sum of these two, grams of carbon dioxide. All right? So to get my 44 grams of carbon dioxide, that's actually 1 mole. I'm going to then need 1 mole of this and 1 mole of that. So I can look on the periodic table again and see that 1 mole of carbon, that's 12 grams of carbon, and 1 mole of O2, which is 2 oxygen atoms, that's 32 grams of oxygen. So I put in here 12 grams of oxygen, 12 grams of carbon, 32 grams of oxygen, and I know that I'm going to get in my container here 44 grams of carbon dioxide. All right? So that's how the mole becomes useful to us. Now, like we said, it doesn't have to be just grams of atoms. It can be grams of molecules, knowing how many molecules or how many grams of given materials that I would want to have, right? For example, if I have a chemical reaction where I'm combining silver chloride with sodium nitrate, right? And I want to make sure that I have equivalent masses of these so that I'm combining them in a 1-to-1 ratio, right? I can find out how many grams there are in 1 mole of this and how many grams there are in 1 mole of that, and identify what the correct ratio of the mass of these different materials are. Okay, so ionic compounds, same thing. These are ionic compounds here. One ionic compound, a mole of it, has 6.02 times 10 to the 23rd units of it, right? So here's a compound. This is CHCl3, chloroform, right? I can tell that there's 1 carbon, 1 hydrogen, and 3 chlorines by the chemical formula, by the structure as well. Adding the mass for 1 carbon, the mass for 3 hydrogens, 1 hydrogen and 3 chlorines will give me my molecular mass. I call this a molecular mass because this is a molecule. How could I know that CHCl3 was a molecule, Fred?
You mean because it's made of nonmetals?
That's right. So that's a molecular compound, so I can call it, I can identify it as its mass as its molecular mass. All right, here's another one. Same system, chemical formula, 9 carbons, find the mass, 8 hydrogens, find the mass, 4 oxygens, find that mass. And again, this 12, 1.008, and the 16 are all coming from our periodic table, right? The masses for those individual atoms. And this is how many grams you need if you want to have 1 mole of that given material. Here is an example of a compound which is an ionic compound. What do you call this kind of a structure here?
That's sodium chloride?
Yeah, but the form in which this structure attains. Sodium chloride is arranged in a what?
A 3-dimensional lattice?
That's right, a 3-dimensional lattice, right? So we have sodium ions and chloride ions. We just take the mass of a sodium and mass of a chlorine and add those together, and the result is we don't call it the molecular mass, we'll call it the formula mass, right? Because this is not a molecule. Does that make sense?
Yeah, but did you take the mass of the sodium ion or the sodium atom?
Well, that's a good thing to think about. We took the mass of the atom, which is here on the periodic table, sodium here, and the chlorine over here, right? And because the mass difference between atoms and ions is never significant, it won't matter. You can always just use the mass on the periodic table.
Okay.
So let's see if you can find the formula mass of this compound.
Don't I just add it all up?
That's right. So it becomes important for you to be able to recognize now how many of these different elements there are represented by this expression. Add them all up carefully in your calculator, and then identify what the formula mass is for this compound. Let's see if you know the name of this compound. Do you know the name of that compound, Fred?
That's barium, right?
Yes, barium.
And are you getting the yeah, I need that.
Okay, so you need the polyatomic ion chart, right?
Yeah, I forgot the name of that thing.
Okay, good. So if you forget the name, or even if you just use it, you should always, anytime you see one, remember we made a promise that every time we see one, we would bring out our periodic or our polyatomic ion chart to remember the name.
It's phosphate.
Very good. So this compound's name is barium phosphate.
Yeah.
All right. So everybody at home, add up the number of bariums, phosphoruses, and oxygens, and see if you can get the right chemical formula. Okay, did you do it, Fred?
Yeah, I did it.
What'd you get?
I got 600. Yeah. 600.2.
Or 602?
Yeah, yeah, yeah.
Okay, good job. All right, so that was 3 bariums, 2 phosphoruses, and 8 oxygens. Is that right?
Yeah.
All right, next one. What's the name of this compound, Fred?
That is, do you have the polyatomic ion chart?
Yeah, let's bring that over here.
There's the ammonium ion. Was that one?
Let's scoot it over there. Yeah, that's the ammonium ion. And then what's that other one?
That's carbonate.
Very good. So we have ammonium carbonate. Ammonium carbonate. Where did you see the carbonate?
Oh, towards the bottom.
Oh, there it is. Okay. All right, so ammonium carbonate. How many nitrogens, Fred?
2.
Hydrogens?
8.
How about carbons?
1. And 3 oxygens.
Okay, very good. So the mass, 106? Oh, 96.
96, yeah.
Very good. Excellent. All right, so given that the molar mass of carbon dioxide is 44 grams per mole, all right, now they gave us that. How could we have determined that, though, if they didn't tell us that the molar mass is 44 grams per mole?
We could have just added them up.
That's right. We could have added up 1 carbon and 2 oxygens and taken those numbers off of the periodic table, again, 12, 16, and 16, right, and gotten our mass that there is in 1 molar unit of carbon dioxide. And again, the units are, that's how many grams there are per mole of this material. All right, so given that the molar mass of carbon dioxide is 44.0 grams, what mass of carbon dioxide is found in 1.55 moles?
1.55 moles.
Yeah.
You just multiply?
Okay, so we've worked on some problems like this in the past where we use different kind of units, but it's important to make sure we recognize this pattern of how we use our units. We call it unit analysis or dimensional analysis. All right. We want to start by writing down the units that we're after.
The units that we're after is mass. Is that grams?
Yeah, grams is fine. You can use whatever you wanted to, as far as like kilograms or grams or megagrams or whatever. But it's an indicator here that they're giving us something in grams per mole, so it's probably going to be grams, right?
Okay.
So now we know that we are starting with 1.55 moles of carbon dioxide. So I write that up here, 1.55 moles of carbon dioxide. Okay? And now I'm going to go from moles of carbon dioxide to grams of carbon dioxide. And that's what this setup allows me to do. It allows me to visualize how my units need to change. And I need to have moles of carbon dioxide down here because I know I need to get rid of these units. I don't want these units, I want these units over here. If I know a conversion factor between these units and those units, then I can just put those units I'm after right above the moles here. Do you know how many grams per mole there are?
Isn't that what they told us?
That's right. They told us that there's 44 grams for every 1 mole of carbon dioxide. Okay, very good. So 44 grams per mole. And if we have 1.55 moles times 44, that will be how many grams of carbon dioxide we have in 1.5 moles. 1.55 times the 44.0098. All right, and the answer is 68 grams per mole. We have 3 significant figures, 68.2 grams per mole.
Okay.
Good. So again, You need to multiply it, but it's better to make sure that you know how to set up your unit analysis system, because this will prepare you for answering questions that aren't as intuitive for us. Okay? Good. Way to go.